Thank you for joining us and welcome to our third webinar in our series on integrating dynamic modeling and simulation into your courses. In this series, we feature experienced professors from various fields who share their insights on incorporating dynamic modeling and simulation into their coursework. Our goal is to provide you with a starting point and direction to begin implementing these techniques in your own teachings. Today's webinar will be presented by Dr. Rod MacDonald and will focus on introducing system dynamics effectively into science and technology courses. But before we begin, let's briefly review some webinar mechanics. So you'll see the grab tab in front of you. This is a great spot if you're having any audio problems. Check the audio settings here. And you'll see the questions box below. We will have time for a questions and answers session at the end of this webinar, so please type in your questions there for us. Now let me introduce our presenter today. Dr. Rod MacDonald is currently an associate professor at James Madison University in Virginia. With over 25 years of experience developing simulation models for a wide range of organizations, from government agencies to businesses, Rod's diverse background makes him an ideal faculty member for the ISAT program, where students regularly use system dynamics to address complex problems in a wide range of science and technology areas. We are absolutely delighted to have him here with us today.
Thank you very much. I'll try to live up to that introduction. I don't think I can. I think I'm figuring this stuff out as we go along. And our agenda for today is we're going to have a poll for you folks, and I'm sort of interested in how you folks are using system dynamics in the different courses or the different areas that you're working. I'm going to go through a little bit of a background on the program at James Madison University. At the end, I have links and stuff. I'll share anything I have. All the materials I have, you're welcome to use and to change and to make them suitable for yourself. And I'm going to go through the sequence of what we do here in a semester-long course, which is an introduction to system dynamics modeling here at JMU. And yeah, I'm just going to show you what I do. So if you could do the poll, Hillary, I'd be interested in seeing the background of some of the folks we have here today. And so what it's saying is 33% are teaching system-long or semester-long courses. That's impressive. I didn't realize it was that high. 67% said no. We could go to the second poll question. It makes sense that it's practically flipped, right? The poll says that 22% are teaching just systems thinking, looking at behavior over time graphs, CLDs, link and loop polarity. 78% no. That's great. And if we could go to the third category or question. And it looks like the poll is 55% said yes to this. So that's great too. 44% no. And the last one is, curious, are you using either system dynamics or systems thinking modeling in part of your courses? So 78% of the folks said yes. So I was very interested in that because that's sort of how it started here, is people started using just system dynamics and systems thinking in their courses, and then they sort of moved on, and we ended up growing the program here at JMU. And the first thing I'm going to do is go over what we do here so you have an idea of what our students' background is when they're coming into these courses. So again, it's James Madison University, located in Harrisonburg, Virginia. The whole university has about 22,000 students. I'm in what we call the Integrated Science and Technology program. And this program was started in 1993. We have about 300 students, 38 faculty members. We have 2 who I would call system dynamicists who've been trained formally anyways in system dynamics modeling, myself and Rafat Zaini. And I think everyone in my program, all my colleagues really are systems thinkers. I did not start this program. This program started before I came. And I think I just gave it a heavy emphasis on using a system dynamics modeling in the courses. And we're a unique STEM program. One of the things we try to do is teach students, no one's ever heard of ISAT is what it is. So we need our students to come out and be capable of doing an elevator speech so that they can explain to employers what's going on. And also we recruit students usually after they get to the university. There's not a lot of students who come to our university and are enrolling in our ISAT program. So a little more of the background is when students come into this ISAT program, they take foundations courses. And these foundations courses are covering physics and chemistry, biology, statistics, calculus, things like that. And we actually teach them those courses. They're not going into other departments to get that material. So it's really concentrated on what we're doing here. We have 6 concentrations, which I'll go over in a minute. And students are expected to they'll take courses in all those concentrations. And then their junior, senior year, they're figuring out what they're going to concentrate in. And typically they'll have 1 or 2 concentrations where they're going to do upper level courses in those areas. And what was going on here was the faculty desired to sort of connect everything. And again, it was the systems approach and realizing that our students are going to be generalists with not a phenomenal amount of depth, but a very broad view of the STEM courses. And they wanted these students to be capable of tying this stuff together. And I think that's where the systems approach sort of was the focus of the faculty here. They really wanted to tie everything together. And this just gives you an idea. Yeah, 38 faculty, 300 students. And what I did was I grabbed this. This isn't a slide I made for this presentation. This is what our unit head uses when she goes out and talks about the program, is what it is. And a lot of the faculty are coming from industry and stuff also. They're not folks who've just been in academia since they've graduated. So we have quite the mix of professors in our program. And this is what they're really talking about when it's interdisciplinary. And I think it's important to realize that we sell this as holistic problem solving. We don't go out and say we're doing system dynamics as a selling point. It's the idea that we're really doing holistic problem solving and that a lot of different people can see this and buy in. And this is the statement again that my boss uses when she goes out to show folks what's going on here. And drawing appropriate from several branches of learning. And again, it's those foundation courses that we're using and the different concentrations we have, and that we're looking for solutions for complex problems. And this is what she also uses when she's out there talking about the program. And it sort of gives you an idea of how things are set up. The roots of the tree are our foundations, and the systems and sectors courses are the sort of the root of this. And we have a number of courses that we teach system dynamics in, and we have 4 courses that are required. And the students get a sort of a heavy dose of systems thinking and system dynamics in those courses. And it's anticipated that they will use that stuff when they're going into their concentrations. And they do senior capstones here also, which is over 4 semesters. And the concentrations we have are energy, the environment, biotech, computing, manufacturing, and the social context. It's sort of how do we tie all of these things together? There's the physical system and there's the human system, and it's the interaction that's generating these complex problems that society needs to deal with, and hopefully that we're preparing our students for. So, and again, this is just where I sort of fit into this system. And the 4 required courses are, we have this ISAT 190, and it's an introduction to holistic problem solving. And in this, they're getting background in the program. They're typically freshmen, and we're introducing them to the systems thinking concepts. Then they go through to a 290 course, which they're doing a deep dive into the actual modeling. And in the 390, 391 Holistic Problem Solving Workshop 1 and 2, it's a year-long course that is centered around a topic that students go into. So those are the courses all students in our program are required to take. Then there are electives. They can take an elective on simulation and modeling, and they will do some agent-based modeling in there. They'll do a lot of system dynamics. They'll do model calibration. They'll do sensitivity analysis. Again, it's an elective. There's an elective in the environmental concentration where they can do modeling in the environment. They do modeling courses in there. We usually use Andy Ford's book on modeling the environment. And some students can do a capstone and use system dynamics. I've had a number of students do that, ranging on things from human trafficking to drinking and driving. And then I also go out and in other classes or teach systems thinking and some system dynamics modeling in the business school, just as a guest lecture, the same thing in public administration. So the idea is that I want to spread the word so that folks are comfortable with what we're doing over here and hopefully grow the field that way. And this is the definition that I use and the program is using for complexity. And we all know there's detail complexity. You're going to have a lot of facts, a lot of things such as building an aircraft, something like that. But what we're really focused on is this idea of dynamic complexity in our program. Dynamics meaning something's changing over time. It's going to involve feedback. There are time delays. There are nonlinearities. And I think if you look at the system dynamics literature, the thing we're adding here is multiple stakeholders. Being able to see things from different perspectives is very important in our program, and hopefully we're getting students capable of doing that. So that's the definition we use and hammer in to all of our students starting in the first class they take in this sequence. And this is the first class. It's just an 8-week course. It's 1 credit hour. And I focus on the beer game, fish banks, and En-ROADS. The beer game, it fits in with our manufacturing sector. It is going to show them the time delays. It's going to show them the interaction between the human system and the physical system that actually exists in the game with the moving of the chips and stuff. I do fish banks for environmental purposes. It's important that they understand the tragedy of the commons and how they are contributing to these problems. We also show feedback loops in that. And when I use En-ROADS, it's really to put them in a different stakeholder role and to realize how they're dealing with these complex problems and how people can lock into viewing things from a particular point of view. And in this class, what I hope they come out with is an understanding of behavior over time graphs, that they can build causal loop diagrams, that they understand link and loop polarity, and hopefully they're going to have some concept of time delays in these complex systems. And I'll go to 290 in a minute, and that's the one I'm going to focus on in this. But we have this ISAT 390, 391, and the prerequisites are that they've taken the 190 and the 290. And this, again, is a year-long sequence. So once you sign up for a particular topic of 390, 391, you are locked in. So it's going to be the same class taught from 1 year to the next. What's unique about this is it's taught by 2 professors, and we try to get them from different subject matter areas. So this year, for example, I'm teaching the Virginia energy transition, and we have one of our professors who's an expert in energy. And we've been teaching this for the last 3 years together, and it will end this year. The topics change every couple of years. We have multiple professors who are teaching these types of courses, and they sort of just roll. It's sort of really unique to have the students for a year. So it's sort of just a great program. In the first semester, what they're doing is they're learning about the subject matter areas. Some of the kids may not be energy experts, for example. So we're teaching them the basics of energy, and then we're rolling into the systems concepts, and they have to be able to come up with a clearly defined problem statement, behavior over time graphs. They're going to write a formal paper. They're going to develop the causal loop diagrams, and this is going to set them up for the second semester. They will have gotten into teams very early in the first semester, and they are on those teams for the rest of the year. And a team size is typically 3 to 5, depending on the size of the class. In the second semester, again, they're with the same teams. What they're going to be doing is developing a system dynamics model to analyze the problem and to sort of start testing policy solutions with that. We require them to develop a user interface for their model. They're typically doing presentations to outside experts, and they will be writing a full report, and they will be documenting their model at the end of this. And we leave, so they're doing all of this in Stella, of course, and the user interface is in Stella, and I leave their user interfaces up online so that if they're on the job market after this or anything, they can point back to some of the work they've actually done, particularly the idea that working on a team for a whole year and the challenges that they faced overcoming that. So the topics are, we've done climate change in the past, we've done agriculture. Right now, the Virginia energy transition is occurring. At the same time, the modern university is occurring. I have a couple of colleagues teaching that. Next year, the proposals that have been accepted, we're going to shift to the global water crisis and to resource management. And again, it's sort of a case study, and they will be building formal simulation models in these classes. And 290 is what I'm really talking about today. And this is the nuts and bolts of their system dynamics experience, really. And it's a semester-long 3-credit-hour course. It's required of all students in our program. One of the things, I do not teach it in the lab. I teach it in a normal classroom that's set up so we have a lot of whiteboard space. And our students almost all have laptops. And we have a few that they're able to borrow in case someone has a desktop or doesn't have a computer. We're usually able to manage that. It has not been a problem. Again, we use Stella. And what I'm really trying to do, and this is still really a work in progress, I've been teaching this course off and on since 2017 here at JMU. And yeah, we're still sort of always improving and working on any bugs that we come across. So. And this is the learning objectives. And again, these learning objectives were developed before I got here and started teaching this course. And it hadn't been taught before, but they had had a plan before they went through the hiring process and ended up with me. And that first one up there is distinguish between a systems approach versus an event-oriented approach to understand complex problems. They're focusing on the system behind the problem, the iceberg itself, instead of isolated events, the tip of the iceberg. Using the behavior over time of key indicators or dashboard variables to understand the evolving status of a problem over time. Working as part of a team to do research on the problem and developing insights. I think we had a colleague who's since retired, Mike Deaton, who was a system dynamicist who was here. And when he was selling the rest of the department on using a systems approach and guiding them towards system dynamics, I feel he was extremely smart in the way he set it up. He didn't want to force anything on anyone. He wanted to leave options open and be inclusive. And I find in the language he picked, when I read this as a system dynamicist, I know exactly what's going on. But if my colleagues weren't trained in system dynamics, and they're reading this, they can see their view of systems and they're understanding these complex problems also. So it was really brilliant the way they set this up. Continued learning objectives are employing causal links, feedback, stocks, flows to describe the causal structure of the system. Receive and reconcile desperate views for how the system really works. And again, this is really that emphasis on the stakeholders and seeing things from multiple perspectives. Using causal loop diagrams to tell a system story. I really believe that the ability of students to tell a story is extremely important. And that the modeling, and when we get into the detailed modeling, and particularly in that 390, 391 sequence, the students are actually building models that are relatively complex. And because they've built them and walked through and operationalized them, they really have a deeper understanding and are capable of telling those stories at the end of that year. It is very powerful. And again, relating systems causal structure to the problem's behavior over time. Again, it's just all basic system dynamic stuff. And build and validate running simulators of simple and moderately complex problems. And you'll see the complexity of the problems that they're dealing with. And at this level, they're mostly sophomores. And we do feed them a lot of stuff is what it is. So, and again, telling the system stories. And here are my goals for what's going on with this course. And I really want them learning the basic of system dynamics modeling. I want them to be able to see behavior over time and understand the type of structure, the type of feedback loops that are generating that behavior. And I want them not only to see this in this class, but in all their classes, anything they're reading in the real world. I want it to be real for them. Dimensional consistency is very important here in their foundations classes, and then their other courses here. Understanding units and units as a check is extremely important. So the fact that we have the ability to do units checks in the software and hold the students' feet to the fire on this type of stuff is extremely important and appealing to my colleagues. Learn about stocks and accumulations is key. I expect students to walk out and to understand if they can identify a stock when it's increasing, that they know the inflow is greater than the outflow. If it's decreasing, they know the outflow is greater than the inflow. If it's remaining constant in the state of equilibrium, they understand that the inflows and the outflows are the same. Identifying feedback, want them to be able to read articles. We want them to be able to read assignments and assignments in other classes and start to see the feedback in these systems. Again, identifying the stocks, just being able to look at the world and understand where the accumulations are, understanding the time delays that are a result of that. And I consider myself successful, and it happens occasionally, but I want them modeling in other classes. I want them taking the skills they've learned in this class, and they will have problems in their other classes, and they will be able to start modeling some small models to generate the behavior that they're observing or to address the problem that they've been given in those other courses. So starting out, when I'm starting this class out, first thing we do is the Chi-Bob. It's an online simulation that we have. And I really believe when I'm starting this course, I want to start out with a game. I do it in 190 with the beer game. The idea is I want to start engaging them. I want to do something fun, but useful and practical. So we have them read the Chi-Bob case study. And at their tables, we're going to make them do a plan with their table mates. And we're just asking them, what would you do in this case? And they have to write out a plan in advance. What are they doing? What are they going to suggest to the managers of the Chi-Bob? We give them the indicators that they could actually move, and we expect them to map out their anticipated behavior. We want to start getting them thinking about the mental models and what's going to happen. And so they do this all on paper first. Sometimes it might take a whole class to get this done. And then I will save that. It's usually on poster paper. And then they will go to a simulation and start to test their policies to see how they play out over time. And again, the emphasis is on simulation. And then we debrief what happened. And this is just an example of the materials. So the decision making for the simulation record is on the top left here. And we've added cattle into this, into the traditional Chi-Bob. So there are cattle, there's predator hunting permits, there's a deer hunting policy, so there's goals for the deer that they have, and they run it in 5-year intervals. So they'll make a decision, they can run it for 5 years, then they can change any of their decisions. And again, we expect them to fill this out by hand. They're working in teams and tables at their tables in the class. And we have a list of questions for them to analyze in the bottom left. And on the right, what you're seeing is the system behavior over time. We're expecting them to draw these behavior over time graphs of these different dashboard or key variables. And again, it's to compare back to the simulation. And you'll have access to the simulation after this. And the simulation, it's relatively simple, but we do have pop-ups that will occur when they're doing a good job and when they're doing a bad job, which are a little entertaining. The kids find a bit fun. So starting out with the game, yeah, this is the what the user interface looks like. It is relatively simple. It does replicate very closely the behavior that they have been reading about. And the goal that they're supposed to do is try to maintain as many deer as possible. And that would be under ideal conditions. They might get up to 30,000. There are tipping points where the system would collapse then, but they're responsible for moving the sliders to achieve that goal. Yeah, and what I do with the KaiBob too is they'll come back later in the semester and actually build the KaiBob model. So they haven't seen stock and flow structure or anything yet, right? We're just engaging them. One of the slides I use is the Miracle on the Hudson, where it was Captain Scully, and they have on YouTube, you can get just the communication between the tower and the aircraft, and it's amazing how calm they remain. And I'll run that for students too. And the idea is, yeah, why were they remaining calm? And the idea is that, you know, if you're a pilot, you're doing a lot of simulations before you get behind a plane. You're prepared for those types of emergencies to a large degree. And the idea that we really do need simulation. KaiBob also sort of reveals their mental models and where they're off and how they're thinking about things. And yeah, they all fail at this. The question is, can we do better? And again, emphasizing the importance of simulation. After that, what we're really moving to is the behavior over time graphs. And this is lecture mode. And I have a rule of thumb. I don't always succeed, but I attempt to never lecture for more than 20 minutes. And I know I'm failing with you folks now, right? Before I get them doing something. But we're lecturing on the different types of behavior, the importance of the time horizon. I remind them back to the previous course where they played the beer game and the delay from when they ordered until they actually received the inventory. We're going to have them drawing the hoped for and the feared behavior. I want to show these behavior over time graphs in real data also. Energy industry is just full of this type of stuff, and the energy industry does a very good job of doing projections or running scenarios into the future. And then what I have them do is draw a behavior over time graph in class, working in twos, and then I'll go around and they have to explain what's there, and again, getting at telling the stories. There's a homework assignment where they're going to be doing behavior over time graphs from the news. And I'm really expecting it to be labeled appropriately, to have an appropriate time frame, to have the hoped and feared for behavior. One of the challenges is getting students to be thinking that this is sort of a reference mode and we will not always need data for this, and emphasizing the idea that it doesn't have to be numerical. It has to have a sense of increasing or decreasing, but items like morale could be something that we would be drawing a reference for. After that, I'm shifting to link and loop polarity. And this is going relatively fast because the students have had a taste of this anyways in a previous course. I usually spend about 1 week on this. I'm lecturing them on the mechanics. I want them working on link and loop polarity. I want them explaining reinforcing and balancing feedback loops. I have a lot of examples for them to work on in twos in class. And I give them written assignments where there is feedback in those assignments, and I'm expecting them to find that and to be able to draw causal loop diagrams. I'm not concerned about the variable names that they come up with, or if they have what I would call intervening variables. I don't care how messy it is. I really want to make sure it's the link and the loop polarity are correct with those things. And I'm always pulling examples from the news to give them, trying to be as current and relevant as possible. One of the exercises I have them do is I'll give them feedback loops already designed really, and they have to identify the link and loop polarity, and then they have to draw the behavior over time of this. And you can see I've highlighted the number of highways as bold there. And I found that you really need to give them the variable that you want them drawing out, where they typically get lost. And this is just an example of a description of an epidemic. and then the type of feedback loops that they could draw. And again, I don't expect them to be exactly like mine, and it could be messy. There could be different variables that are in there, but I would expect that they would have at least a couple of feedback loops, a reinforcing and a balancing feedback loop from reading that description. And the rule of thumb when you're teaching the causal loop diagrams is that if the variable at the tail increases, which way does the variable at the head of the arrow move? And the heuristic I use is always ask, if the tail increases, which direction does the variable at the head move? Is it going to move in the same or opposite direction? Is it a plus or is it a minus? This is the thing that students get most stuck on. They can do that, but then if a variable goes down, they sort of just crash with that. And I spend time explaining this to folks. I don't know what the solution is. This is a sort of caveat for you folks on what you should be looking at when you're doing this. And if you've been doing this, I'm sure you've experienced this already. So next thing I'm moving to is graphical integration. You'll notice that these probably look familiar to all of you. Over on the left is the mature trees. This is from Barry Richmond. It's a written description of a tree farm that has been harvesting for 50 years. And they have the decision rule that every time I harvest a tree, I will plant a new tree. However, it takes 6 years for the new trees to mature, and we're looking for the behavior of the stock given a written description of what actually are the rates. It's the same thing for this net revenue. They would graph out what is going on with wealth. And the wealth is always growing because the dollars per year are always positive. And then from Sturman on the right, I have the department store dilemma. And there's a series of questions that I ask with those. And this is before I move into the stocks and flows. I want them thinking stocks and being able to identify what stocks are doing. And then the next thing is we're into the stocks and flows. And it's a quick identification of stocks and flows. Yeah, relatively quick. Again, hammering in when stocks are increasing, when they're decreasing, when they're in equilibrium. The idea that these stocks and flows could have multiple outflows, they could have multiple inflows. We're teaching them about using the icons and stuff at this point. Another thing I emphasize with folks is that this is not a course on software. This is a course on learning system dynamics modeling. So I have a lot of videos when we do these models, and you'll be able to get access to those, showing folks how to do things. I walk through step by step. And again, it's not a class about the software. It is a class about learning system dynamics. Yeah, stocks and flows, the dimensional consistency. Another thing we're emphasizing is conservation of mass. It allows me to separate the information from things that are physical flows as well as things that are information flows. But in our program, because we're a STEM program, that conservation of mass is extremely important. I've mentioned it too many times already, concept of when stocks go up and go down. I really want to hammer this into them. And yeah, we're using videos that I've made on Stella. The folks at IC Systems are always updating their software, so it seems every year I'm updating, so I'm using the current version of the software for my students. And again, not a software course. And then we're getting into simple models is what we're starting with. And this is just one example, starting out with the population model. We're getting into the basic equations at this point, and what I'm hammering into the students is that they should be focused initially on 4 types of equations when they're figuring things out. It's going to be addition, subtraction, multiplication, or did I say division already? So it's just the 4, right? Adding, subtracting, multiplying, dividing. That is it. And they're going to have to develop the skills to figure out when they are going to use which, and does it make sense? The units are very important for this. And they start going through a variety of examples that are going to hammer this into them. Again, always the units and directions that are really spelled out very clearly, or as clearly as I'm capable of doing this. And they should be asking the question of why are they getting the behavior. Really want them linking that behavior, that the reinforcing loop in the diagram you're seeing is dominant, and that is why this is growing. And here's one of the other things I found that students really get stuck on, moving from those causal loops to the stock and flows, is the realization that when you have an outflow, it's like a causal link going back to the diagram, and that it's draining out from the stock, and that there is a minus sign there. And I'm torn between using biflows all the time because yeah, I think it looks a little bit messy, but I want them to understand that these things are draining from the stock, and that actually represents a causal connection. The other thing there with the stock is I always require my students to have the plus and minus. I want stocks that can go negative. Population should never go negative. We can't have negative people. But if they've made an equation error, I want to know it, and I want them to know it is what it is. And I'm very thankful that Stella now has the stocks will turn yellow when they're going negative, right? And so will the flows. That's a great indicator, but I want them to, if they make a mistake in the equations they've written, it needs to show up is what it is. So one of the things I insist in is making sure that the stocks are always capable of going negative. So we've run through those simple stocks, and then we have written descriptions. And the way I set this up is I have them working in teams, maybe 2 3s, maybe a group of students at the table, and I throw them up to the board. They have a written description only, and they are to start building the models from those written descriptions. And there's usually about 10 of these that I go through. And again, this is relatively simple. It's just an aging chain for the most part. But what we do here is I've started to switch out. I have fractions, and you can see I have time for some. So the students have to start figuring out, when am I going to be multiplying and when am I going to dividing? And I hope after these set of exercises, they realize if it says time, it's going to be division. And if it's a fraction washing out, it's going to be multiplication. There's also the opportunity to show them how if you take the reciprocal of any of these, you can always switch this. It's actually the same values and generates the same type of behavior. And again, from written descriptions, they're developing this, but in teams, and then they're to take a picture of it and do it as a homework assignment and submit that homework assignment. So, and they will be writing the equations on the board, and they can put the units on the board also. I'm fine with them sharing that type of stuff. And again, we're focusing the idea of structure is generating behavior. And yeah, just hammer that in all semester long. And after we go through all those stocks and flows, we can get goal-seeking behavior, we can get exponential decline, we can get exponential increase. It's time to move on to S-shaped growth. And I do this by moving to a net flow. So I use the same population model, and the idea is that I'm going to be building on this model continuously. So we're moving to an S-shaped growth model, and then this is an example in the learning guide, which you'll have access to, where we sort of spell out exactly how to build this model. And we've given them all the information they need, and the goal is to get them to match up the simulated population to the actual projections, the historical of the world population, as well as the projections from the United Nations. And what we're doing is getting to show them a couple of things. One is how the S-shaped model works, and then the idea that you can match up the historical data. And we have a series of assignments that are based on descriptions of what are S-shaped models. The growth of Instagram users, or the growth of iPhone users, things like that that are S-shaped. And hopefully what they're going to learn is that this structure, you can change the names of it, change some of the parameters, and it will generate the same behavior. And the idea that we're reusing behavior over and over and over again, or reusing structure over and over and over again. And when we're here, we also get to shift over and start talking about loop dominance at this point too. And I think this is a hard concept for a lot of the students to gather. But we want to emphasize that, you know, if you're looking at only part of the system, you're only seeing part of the story. And the idea that some people could be right during certain points in time and other people would seem to be wrong. But as this plays out, it's going to shift. And I don't use so much the loop dominance. I very much like it in Stella, but I like the idea of using the net growth, which on the right is that red dotted line, is the net growth. And when the first derivative of that is 0, is when the loop dominance is actually shifting. So another opportunity to use loop dominance, or to start explaining or introduce loop dominance to students. So once we've run through all these S-shaped growth models, then we're going to start adding additional structures so that we can get overshoot and collapse. And if you recall, we were using the population model. They were able to match up with S-shaped growth to the growth phase and to the S-shaped phase, but they couldn't do the overshoot and collapse. And the idea is if we add structure to this, they would be able to generate the overshoot and collapse in that model. And we do this by adding a resource base that's depleted. And then later on, we add a reinforcing structure that will let it grow. But as long as more is being consumed than is growing, it's going to generate the overshoot and the collapse. And again, we'll give them a number of examples with this. And the key is we want them capable of generating all 3 behavior modes here. And the overshoot and collapse, you can see the blue line is the simulated. And the number 2 red line here is the data that comes from the UN. It's actually a projection going into the future. So, and the focus is on the behavior. There's going to be numerical differences with this, and the students tend to get stuck on that. What's the right answer? And I think with this approach, we're trying to get them to focus on the structure and not to worry as much about exact numerical answers. It's the behavior that we're concerned about. And then when we shift to the predator-prey model, I show them the Lockton-Volterra model. And I actually write this on the board, which tends to scare them, the differential equations for this. But then we will go in and build the model using the X's and the Y's. And I have them pick values, and we back into a model that's in equilibrium. And then I can show them how it gets out of equilibrium. And this is the model we end up building together in class on the board. And you can see I've renamed the variables, but I've kept the labels of A, X, and Y and stuff that they had. And we typically start out by saying, you know, give me the predators to the prey. We're in an environmental program, or a lot of the kids are, so they understand there's going to be a certain ratio between predators and prey. They'll give us that, and then we'll back in and have them come up with a prey birth rate. Could just be a wild guess. And from there, if we want an equilibrium, we know the inflows have to equal the outflows. We have the 2 stocks. We can start backing in and solving for the unknowns. And then when we knock it out of equilibrium, all of a sudden we have a system that's oscillating. It's an oscillating system will require them to go and make it Runge-Kutta floor, but they're getting into oscillation. And at this point, we are back to the chi-bob. I'm going to have them build the chi-bob from scratch. And the way we do this is we give them the stock and flow diagram, and then there's a written description where they have to fill in things. So the physical description of the deer population is left for an exercise, and on the far right, the units are left for the exercise. And this would walk through the whole chi-bob model, and they're going to have to do it that way. And with the chi-bob, we do have, I don't know if it's data or information about the eruption in the chi-bob plateau in the mid-1920s. So we have them go to that. And now, instead of using that interface, they're going to be using the model to test the deer hunting policies. I'm going over nonlinearities at this point so that they understand how to build those graphical functions and how to set up nonlinearities. And we're sort of kicking them out the door to a degree. They have to start understanding the feedback and tell the feedback story and what feedback loop is dominating what or when. And then they're trying to generate these different behavior modes. And then we're to a final project. The semester's just over, and I'm going to show it. We have a number of examples that we will give the students opportunities to get. What we've been focused on lately is the flu epidemic. We started this in 2017, and I have them do it in 2 weeks. Some of my colleagues do it over 3 weeks, and it's built in stages. There's a written description. We give them stakeholder roles. And as they're building this in sections, there's 6 stages. And at each stage, they will complete their model and they should be able to generate behavior. And there are a link in the written descriptions where they go to IC Systems and see the model and the behavior that we have up online. And it's anticipated that before they progress to the next stage, they need to be able to replicate the behavior at the previous stage. We're going to have them test policies, and then they're going to make a poster, and then they're going to tell a system story from a stakeholder perspective in a final. Sometimes we bring them into a room, they have posters up, some of our colleagues have come by and ask them to explain what's going on. Other times we might skip the posters and they will just be there, but we're going to ask them to explain what's going on in the model from different stakeholder roles. And just like the KaiBob, we are spelling a lot of the stuff out, but there's pages and pages of this where we're leaving some of the stuff for exercise, and in other cases, we are giving them the information that they need in order to build the model. So it's a combination of things. Oftentimes, they'll have to figure out the equations on their own. And I'm just going to pull up my Stella model very quickly of this to give you a quick example. And if you're still sticking with me, so this is the actual model. And if we wanted to turn this into a COVID model, if we ran it from recovery back to susceptibles and ran it over a different time frame, it would oscillate like COVID. I'm going to the user interface right now that students would be going to. And oops, this is for each stage that they would have access to one of these. And there we go. And you can see that they have a simulation model that they're capable of running. It's a relatively easy user interface. They can click and look at the system structure, make sure that they're close to what they have. And they have an assignment with this, so what we're asking them to do. And they're capable of simulating this. This model remains online at all times, and you folks would also have access to that. I'm going to go back to my slides. And so this is really the course outline. Start with a game. I want to do something fun. And then I'm rolling into the behavior over time graphs. They would have seen this before. We're spending time on that, getting them to do it on their own, hopefully doing readings from newspaper articles and stuff and finding that. They're going to do the same thing with CLDs, identifying the link and loop polarity. And again, I have found in my experience and in my consulting experience, colleagues and I will build a model of the same problem, and they sort of look very different. We may have different variable names, we may have different intervening variables, but when you look at the feedback structure, it's pretty much all the same. And if the feedback structure is the same, I consider that we're really modeling the same thing. Those other things are just window dressing. I go to graphical integration. Then we're moving on to the stocks and flows. We start with a series of very simple models that they build up on. We're focusing on the dimensional consistency. We have additional stocks when we move to the net flow, additional examples that are becoming a little bit more complex. Then we're moving to the S-shaped growth, focusing on loop dominance there, and the idea that these things can grow, again, applying them to written descriptions that are from the real world. We're moving to overshoot and collapse, and then oscillation, then the final project. And the idea is that there are 6 modes of behavior, right? And that they will have had structure capable of generating these 6 modes of behavior. And that when they're in their other classes or running the problems, if they see data that looks like that, they should be able to refer back to this to understand what's going on. And here are resources. What we have is it's on Pressbooks. It's really a work in progress. We call this the System Dynamics Learning Guide. It was written by Mike Deaton and myself. And what happened is Mike sat in on my course when I was teaching this and started taking notes. And this developed into this learning guide, which is, it's close to 200 pages now, that has the examples and stuff. So what I've run through here is available. And the idea with this learning guide is that people would be able to take it and re-engineer it for their courses. And we're thinking right now it's sort of focused on the environment, but could we make it for energy? Could we make it for manufacturing? Could we make it for biotech so that it would fit in with the concentrations we have at JMU? And then it's still disorganized. I've been scrambling, folks, apologize for that. But there's a Google Doc with this link. It should be shared. Okay, so you can go, and I haven't filled out all the materials, but the materials I showed you today and the models that I have and the assignments that I have are all in there. And my email address is at the bottom. And I'm giving you permission to bug me. Last semester, I taught 5 classes, and this semester I'm teaching 4, so I've been doing overload. They've all been system dynamics modeling. I love doing this, so I really want to promote the field. So I've talked too much. Folks, questions, I guess, is what we're looking for now. Hillary?
Okay, there are several questions. So the first one, do you have suggestions for how to introduce SDE modeling into in the context of a 1-semester course that is focused on a particular topic, in this instance, food systems sustainability? In that case, students have topic-related training, but not necessarily SDE modeling or systems thinking training.
Yeah, so I would argue that if you look at the learning guide, if you could go through and substitute those examples with examples from food systems, you would sort of be off and running. And I think that's extremely beneficial, and that's what we really want to do because it relates to what they are teaching. And we're using system dynamics as a tool so that folks are learning more, and sort of on the side, they're learning about system dynamics and those concepts that are important. So I think this outline that I have here of walking through, I don't know of any food games, but walking through the behavior over time graphs and all those examples, if they were related to food systems, would be the way to go.
Any surprises that you learned from students during or after an SD class?
Any surprises? I'm really still, they really get stuck when they're drawing causal loop diagrams with that rule of thumb. If the tail goes up, what direction does the head move? They can do that without a problem. And then when you tell them the tail has gone down for whatever reason, they start switching the signs. And it's like, no, no, no. I have not figured that out yet. I don't know what to do with that. Some of the surprising things is that students are using this stuff in other classes. And I can tell you, nothing pleases me more than when they'll come to me and they're doing a project in another class and they're asking for some help on a model. I think that's the biggest deal. I think that's when I have them hooked. And I think the students sort of fall into 2 categories. Some folks, it's like, this is just painful. They can't wait till they're done with Rod's class. And others, it sort of clicks with them is what it is. And I don't know what the solution is. I understand that people aren't going to be as passionate as I am about this. And I am comfortable with that. So if they walk away thinking in time delays and stocks and that there's feedback in the world, I consider that to be a success.
What kind of jobs do your students find?
So because we're in a STEM program, a lot of them go into consulting. We have a student now, he was very good. He took all the courses. He did his capstone on energy modeling. He went to the state energy department. And then he works for Governor Youngkin right now. So a lot of them are pretty much going into consulting work when they graduate. They've had a lot of system dynamics, but they've had a lot of other things. And the idea is that they're supposed to be able to communicate. They can talk to experts who are engineers or computer programmers, and they're going to understand the social context and how these systems work and be able to explain those complex systems or the technology to different types of managers in order to solve problems. So a lot of students go into the environment. We've had a lot of students go into the energy field, and a lot of the students are going into consulting.
Which version of the modeling software are your students using, desktop or Stella Online?
They're using the desktop. I require them to purchase Stella Architect. I suggest that they purchase the version that is perpetual. Most of them don't. And over the years from the university and from my own consulting funds, I have built up a number. I have a bunch of student licenses, I guess is what I'm saying, that I can assign to students. And I pretty much tell them, I don't want to be paying for your beer money, but if you're really stuck, I'm happy to share with you. I found the secret is to get them purchasing the software in the first week or two and get them modeling quickly. If they wait too long, then the students tend to be broke. They spent that bookstore money and it's gone, and then they have trouble. So we use Stella Architect is what we're using, yes.
What is your advice to minimize effort for grading student work deliverables?
Yeah, I'm not sure about that. I mean, so a lot of what they're doing is submitting models is what it is. So with the software, I'm looking, I know, does it create the correct behavior? Are the units right? So it's very nice having those units checks in the software. I do want to have them writing and answering questions, but that's the time consuming part. What I have is I have a lot of quizzes in the class, and we use Canvas, and I'm able to have diagrams and stuff in there, diagrams of models, where I could put a model in there. If I put the S-shaped model in, I could have a variety of graphs and ask them which type of behavior is going to be generated by this. So that type of stuff is relatively easy. It's the tough stuff is when I have them writing out answers to questions that it takes a little time to go through those. I really haven't figured that out yet. Yeah, grading is the toughest part of this job.
Do you teach discrete event simulation? And if so, in what context? Batch manufacturing or patients traveling through hospitals?
I have not. I'm sort of the hardcore system dynamics guy who wants to focus on continuous things. I have students right now who are looking at small nuclear reactors and are insisting that they come online all at once. So we are doing that in the form of a batch coming through. And I think we've used the queuing function in Stella for stocks in order to capture that correctly. But for the most part, we're not doing that. I'm arguing that we're looking at this at enough of an aggregate level that we're taking that continuous view so we don't get too much into the discrete event simulation.
How many students do you work with in a modeling course, and how often do you meet in lecture settings?
So the lectures are 2 times a week, and the class size we have a cutoff of 25, but if I have additional students, I usually let them in, but it's been around 25 lately. The unique course is at 390, 391, and what I require students to do, I never lecture in those series of courses. It's really pretty much students working in class, and when we get to the second semester of modeling, I require students to meet with me in their team for an hour to an hour and a half outside of class, and we have the model on the board, and together we're adding structure, and I'm pushing them on that type of stuff, and then they're expected to go away for the week, and then they come back with additional structure, additional questions, and we'll build that out for 8 or 10 weeks, and then they're testing the model and writing up the reports. So I know that's not many professors would do that, but there is no prep time for that class, and all the projects are different. So this year I have 9 teams and I have 9 different projects, all related to the energy transition in Virginia.
Has any other departments in your university picked up SD?
To a degree. I think one of the things is I have them sit into my classes and they decide it might be a little too hard to jump in. But our public administration program is doing systems thinking, and I've been working on it with some of their students, doing a project for the local community where we're building a formal simulation model. And in our business school, I go over and run the beer game for those folks, and they do a little bit of modeling, but not so much yet. Actually, we have an intelligence analysis unit that has gotten into the systems thinking and would like to do modeling. And if I can, I would co-teach a course with one of them. We're planning this for what would be the spring of 26. is what we're thinking of offering a course where they would do, yeah, modeling like I've showed you here today.
Great. Well, thank you very much. We have run out of time for today. This is recorded, so you will all get a notification in about a week that the recording is up and available for everyone. And we will also have the links available that Rod has included in this as well available for you. So thank you again, Rod, for joining us. And we hope everyone comes again for a subsequent webinar.
Thank you, folks, very much. Feel free to reach out. Feel free to bug me because I'm a little bit busy, but I really want to promote the field. And if you're using it and I can help, I'm willing to help.